Okay, folks, we're going to come back together as a class and work through some of the finer points of this problem. So there's some nuances to this problem, and there's a lot of stuff that you're already familiar with, and you can work your way through just with your given skill set already with SCLEPS. Okay, so I did ask that you write this in your notebook, do that on a sketch in the coordinate system in the list. I'm going to go ahead and shrink these words now because I want to use this space to work, and I don't want to be writing all over my own writing. So I'm going to come over here and just shrink that down, okay? And then I'm going to go ahead and get caught up to you guys and draw my balloon. Okay, and then here's the little package. And the balloon is ascending, right? The balloon's ascending. So maybe an arrow for that. Does that make sense? Okay, now when it comes to the coordinate system, you actually, remember, you're the physicist, you get to pick where you want to put your origin. And for most of our work before the winter break, we just tended to put the origin wherever the object was at the beginning of the problem. And you could still do that, right? You could put your origin right here. But we do know that this package is going to fall down, right? And so what that means is if you put your origin here, then all your positions are going to be negative. Which is fine, but it's just like an additional thing to keep track of. So one nice little hack, when you work with free fall specifically, is to pick the origin to be the lowest point in the problem. All right, let me say that again. Pick the origin to be the lowest point in the problem. Okay, so I'm going to draw the ground down here. They did tell us that the package gets released 79 meters above the ground. Okay, and then what I come down here is I call that 0, and then I write down up as positive, like that. Make sense? I would just go ahead and have you change your origin if you haven't done so already. It's going to make everything easier as we work through the rest of the problem. Okay? All right. So here comes the surprising part, all right? Because I asked you to trace the path that this package takes when it's released. And all the paths I saw looked like this. Or maybe like this. Okay, but those are all incorrect because they're missing a small but crucial part of the motion. Let me try to simulate that motion for you right here. Okay, so here's the 79 meter mark. My arm is the balloon. This white erase ink is the package. Okay, and I want you to notice the motion of the package. So what I'm going to do is I'm going to pull my arm up like the balloon's rising, and right when I get to 79 meters, which is my hand, I'm going to let go. And I want you to notice the motion of the package, quote unquote, right after the release. You ready? Remember, I'm releasing it here. What are you seeing that's not in your drawing? It's going up and then down. When it's released, it has the same upward velocity that the balloon did. So it has to first lose that upward velocity before it falls down. So let's update our drawing, right, our little dotted path, to show, it doesn't really move sideways, but we're going to go ahead and go like that just to show that it does go up and down. And you can see that more clearly. Right, so it's not going to go out like that. It's just going to go straight up and down, but we want to draw it like this just so we can see it. So I want you to show that little bit of upward motion. All right. Now we'll go through XI, XF. Delta T, VI, VF, A. The usual suspects. Still constant accelerated motion problem, so we can still use our same tools from before. I'm going to point to the value. I'd like you to call out to me what that value is based on the information of the problem, or you could say question mark, unknown, something like that. All right, XI, 79 meters. XF, 0. Delta T, question mark. VI, 10. I'm going to go ahead and write positive 10 just to illustrate that it's going up, right? Consistent with up is positive. Final velocity? Question mark. So the final velocity, let me be clear, when we talk about final velocity in free fall, we are talking about the instant before it hits the ground. Obviously, after it hits the ground, it's not going to be moving anymore, but the interaction with the ground makes it not be free fall. So when we say how fast is it going when it hits the ground, we mean that instant before, when it's moving as fast as it's going to move before the ground stops it. So we don't want to put 0 here, we'll put question mark. And what about acceleration? Excellent, the negative, right? Negative. So here, yeah, we are, so because it's, we are going to use a calculator today, we're going to revert to 9.8 meters per second squared. But hold that thought on the 10 meters per second squared. Because now we can do a bit of estimation, right? So I want to show you the power of the pattern from yesterday in working these types of problems. The first question we're asked is, how long does the package take to reach the ground? That's how much time, right? Well, we could estimate that counting by tens, right? Let's try it. If I start with 10 meters a second upward speed, how fast would that package be going 1 second later? But for these estimation purposes, we're going to round 9.8 to 10. So 0. So it's going to take 1 second to get to its apex. Now, for the next question, how far does it travel in that 1 second? Upward. But it would only cover 10 meters if it kept that 10 meters per second the whole second. Holden?
5 meters.
How'd you get that answer?
Because after 1 second, it's going to be moving 0 meters per second, and average of 10 and 0 is 5.
For 1 second.
For 1 second.
So it's very natural to just be like, oh, it's moving 10 meters a second, so it's going to go 10 meters. But it doesn't keep that 10 meters a second, right? It's slowing down the whole time, and so that you have to use that average velocity, remember from yesterday? So the average would be 5 meters a second for 1 second. So it goes another 5 meters, right? Well, it was already 79 meters high, so let's just call that 80, right? Because we're estimating. 80 plus 5, 85. So now it's 85 meters high after 1 second. So now we have to work our way down. We're working on this example problem from the board. All right, just copying it into your notes.
Okay.
So let's try this now. Let's talk through this together. This is the pattern from yesterday. How far, so now it's at its apex. How far is it going to travel in the next second? Went 5 meters up, 5 meters back down. So now it's back where it started, right? That's 2 seconds. How far is it going to travel in the next second? It traveled 5 in the first second. 15. So now we're at 20. How much? Then what? 25. So 20 plus 25 is 45. And then 45 plus 35 is 80. So if you add up all those seconds, right? 5. Well, we did 5 up, 5 down. Then we're at 20 down. Then we're at 45 down. Then we're at 80 down. So after 5 seconds, we're pretty close to the ground. So you could kind of, as you do this a little more, you get a little more comfortable with it. But we already know without any calculation that we're looking at about 5 point something for our answer per seconds. Okay? So that would be an example like if you you probably won't want to do this every single problem, right? But let's say you're taking a quiz or a test and you kind of just feel suspicious about your answer that you got on the calculator, right? You could try to check it this way. So, something to think about. But let's proceed with the way we would do this in a SCLEPS fashion. So we've done SEL. I guess the L is here, right? And now we're ready for some equations. Well, let's see what the first question asks us. It says, how long does the package take to reach the ground? Right, so we're looking for time. Let's look over at our equations here. What equations have time? Which one would you like to use? For time, which one would you like to use? Wouldn't you like to use equation 1? Right, because that's a simple one. But we don't have VF and we don't have time, so that doesn't work. So technically you could use this equation here, but I basically forbid you, you have to use the quadratic equation to solve it. I basically forbid you to use a quadratic equation in this class. You should never have to use the quadratic equation in this class. Yeah, hold it.
So could you solve for the final velocity first?
Good, using equation 3, excellent. So we're gonna, we see that since equation 2 is out, I'm not going to allow you to use the quadratic to solve. That means you have to use equation 1. But if you're going to use equation 1, you need to final velocity. So 2's out, want to use 1, can't use 1 until I get final velocity. What's left? Oh, equation 3. So we're going to try equation 3. All right, and then, so you should be able to plug all these in, right? So that's, you'll be able to solve for the final velocity. And then I'm going to just go ahead and over here, I'm going to write that equation. Once you get your answer to this, then you can plug it in here and you get your answer to the total time. Okay, so I'm going to give you a few minutes right now to work through that. And then we'll check answers. You may.